Hello, and welcome to Concavity and the Second Derivative Test. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This lecture is for Math 1411, Calculus at UTEP, and it comes from Chapter 3, Applications of Differentiation, and Larson's 11th edition Calculus. Concavity and the Second Derivative Test is Section 3.4. So what is concavity? Let's let f be differentiable on an open interval I. So, always the derivative has to exist if we're going to be talking about using the derivatives. The graph of f is concave upward on I if f prime is increasing. So the first derivative is increasing on the interval, and it's concave downward on I if f prime is decreasing on the interval. Now remember, this is talking about the derivative increasing or decreasing. To talk about the derivative increasing or decreasing, we have to be able to find the second derivative, f double prime. So we can look at really what this means. If our slopes, positive slopes, and they're decreasing, so this is pretty steep, it's getting less steep, along the way negative slopes, getting bigger negative numbers, steeper and steeper. So concave up, steeper and steeper and steeper as they're positive, less steep and less steep and less steep as they're negative, because of the way positive and negative numbers work out. So my test is, let f be a function whose second derivative exists on an open interval I. If the second derivative is positive for all x and I, then the graph of f is concave upward. So positive, concave upward. Concave up looks like these ones in red down below. If the second derivative is negative for all x and I, then this graph is concave downward. Concave downward, slopes are decreasing. Alright, so we're looking at the second derivative, and this is a lot like increasing and decreasing, how the first derivative tells us about the function f, but now the second derivative tells about the first derivative increasing or decreasing, which then leads to concavity in the original function. Now, we had critical numbers when it comes to first derivative. Now we're going to have what are called points of inflection. Let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point, and what that means is, if the first derivative exists at this point, tangent line, slope of the tangent line, slope is the first derivative, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward, or downward to upward at the point. So like we had the extrema, where we change from increasing to decreasing or decreasing to increasing. For the second derivative, we call it a point of inflection. So here's theorem 3.8. If c, f of c is a point of inflection on the graph of f, then either the second derivative is 0 or the second derivative does not exist. So you can see, really, it is the matching idea of a critical number, only it's for the second derivative, and we'll call it an inflection point. So concavity changes at an inflection point. It's not necessarily something you can see until you know you're looking for it. We can see a minimum, we can see a maximum, but where the concavity starts changing, now that's what we're looking for when it comes to an inflection point. So let's look at examples. Let's determine the open intervals on which the graph is concave upward or concave downward. Start with polynomial, f of x equals negative x cubed plus 3x squared minus 2. I'm going to take my first derivative because that's the only way to get to the second derivative. My first derivative is minus 3x squared plus 6x minus 0 if you so desire. The second derivative, the derivative of minus 3x squared is a negative 6x. The derivative of 6x is 6. This is a polynomial, so I know the second derivative exists everywhere. When I set the second derivative equal to 0, 0 equals negative 6x plus 6. Let's add 6x to both sides. Divide by 6, and I get x equals 1. We're going to use the same number line approach that I did for increasing and decreasing functions and our critical numbers. So using x equals 1 as our possible point of inflection, my second derivative is negative 6x plus 6. I'm going to take a test value 0 to the left of 1. I'm going to take a test value 2 to the right of 1. And I'm going to evaluate these test points in green in the second derivative. I want to know, is the second derivative positive or is the second derivative negative? When I put in 0, I will end up with a positive value. When I put in 2 to the second derivative, that's negative 12 plus 6. I don't care that it's negative 6. I care that it's negative. And so, positive, I might say positive. Positive people smile. It's concave up. Negative people frown. It's concave down. Whatever silly little tricks work for you, that's what works for me. So once I know the second derivative is positive, it's concave up, negative infinity to 1. Once I know the second derivative is negative, it's concave down. I could write my interval for concavity, concave down. Since we do change concavity at x equals 1 is the location of a point of inflection, but I have to put it into the original to find the actual point of inflection. Another polynomial, y equals x to the 5th minus 5x plus 2. My first derivative, 5x to the 4th minus 5, and my second derivative, 20x to the 3rd. We know the second derivative is 0 when x is 0. And since it's x to the 3rd, there's just one term. We know that when x is positive, the second derivative will be positive. When x is negative, a negative to the 3rd power, we'll end up with a negative second derivative. So without even using a number line, just looking at our second derivative, I know that I'll be concave up on 0 to infinity, concave down on the left side, so negative infinity to 0. You don't always have to use a number line. It's a tool to help you, but if you don't need that tool, you don't have to use it. It's not something you have to show, unless, of course, you're taking a different class with someone else and they tell you have to. Then, you should do that. Alright, polynomials are so boring. Let's do some rational functions. F of x equals x squared over x squared plus 1. Unfortunately, to find the second derivative, we must first find the first derivative. To find the first derivative, we're going to use the quotient rule. So we'll have f prime of x equals x squared plus 1 times 2x minus x squared times 2x all over x squared plus 1 squared. If you need a review of the quotient rule, you should check that out. That's from one of my earlier lectures. That sounds like chapter 2 quotient rule, probably section 3. Chapter 2, section 3 sounds about right. And this is fine. The basic low d high minus high d low over low squared is fine unless you're going to use it. And since we need to find the second derivative, we need to do the algebra and simplify our first derivative. Distribute the 2x. Combine like terms, I have 2x cubed minus 2x cubed. So I'm left with the 2x in the numerator, x squared plus 1 all squared in the denominator. And of course, now to find this derivative, so I can find my second derivative, I'm using the quotient rule with a chain rule built in. So that's x squared plus 1 all squared times 2 minus 2x times the derivative of the denominator is 2x squared plus 1 times 2x. This 2x, derivative of the inside. Don't forget the derivative of the inside. And when I square my denominator, now it becomes the 4th power. Let's see how that simplifies. So now we have to simplify this second derivative. And when I'm simplifying this second derivative, it's kind of a nightmare. Notice that, let's go in blue here. If I take out one of these, an x squared plus 1, and an x squared plus 1, and an x squared plus 1, right from all three places, I now have an x squared plus 1 to the 3rd in the denominator. In my numerator, at this location, I'm left with 2 times x squared minus 1. I've taken out the x squared minus 1, so I have 2 times 2 times 2, which is 8x squared. And then when I combine like terms, I'll have 2 minus 6x squared all over x squared plus 1 to the 3rd power. Now, this denominator, because x squared is always 0 or higher, when I add 1, that'll be 1 or higher. And a positive number cubed is going to be positive. My denominator is always positive. I have no undefined points. When my numerator is 0, that tells me that x squared is 1/3, which means that x is plus or minus the square root of 1/3. And if we rationalize that denominator, right, the square root of 1 over the square root of 3, it becomes plus or minus square root of 3 over 3. So I have my possible points of inflection. I have a test value to the left, a test value in between, and a test value to the right. Remember, I could use any values I want. I just want to make sure that square root of 3 over 3 is less than 5, and I should be good. So when I use the test values, I'm going to use my test value of negative 5 in the second derivative. And we have already established the denominator is always positive. So when I put negative 5 in, negative 5 squared is 25. 2 minus 6 times 25, don't care what the number is, I care that it's negative. And a negative divided by a positive is negative. So this is going to be concave down. When I put in a 0 in the numerator leaves me a 2. 2 over a positive is positive, so we're concave up in the middle. And again, whether it's a negative 5 or a positive 5, when I square it, I get 25. So f double prime of 5 is also negative. Now I know my my concavity. I'm concave up between the two possible points of inflection, and concave down on the outside. So negative infinity to negative square root of 3 over 3. Don't forget a little comma or something in between. And then square root of 3 over 3 to positive infinity. Now, second derivative test. Of course, this uses the second derivative, but what is it testing for? Let f be a function such that the first derivative is equal to 0. So it's a critical number of the function. And the second derivative of f exists on an open interval containing c. All right, so the first derivative is 0, and the second derivative exists. So if the second derivative is positive, then the graph of f has a relative minimum. Why is that? If the second derivative is positive, I'm concave up. If the first derivative is 0, it must be a minimum. Similarly, if the second derivative is less than 0, it's concave down. And so I must have a maximum. Unfortunately, if the second derivative is also 0, the test fails. It may be a maximum, maybe a minimum, might not be either one. In the case where the second derivative test fails, go back to the first derivative test and see if the graph changes from increasing to decreasing or decreasing to increasing there. So, let's find all relative extrema. Use the second derivative test where applicable. Our function is negative x to the fourth plus 24x squared. The first derivative, negative 4x cubed plus 48x. We know the first derivative will give us critical numbers, increasing and decreasing, and extrema. So I'm going to factor out a negative 4x. I'm left with an x squared minus 12. Negative 4x times x squared minus 12 equals 0 tells us x equals 0. Or x equals plus or minus the square root of 12. But we know the square root of 12 is the square root of 4 times 3, and we know the square root of 4 is 2, and we're left with the square root of 3. That's how we get our two other critical numbers. Now, I want to use the second derivative test. So I'm going to take the second derivative, especially for a polynomial. That's quite easy. That's negative 12x squared plus 48. The second derivative gives us the location of points of inflection, concavity, and extrema classifications. So now I'm going to set the second derivative equal to 0. Add 12x squared to both sides. Divide by 12. X squared equals 4. Tells me x equals plus or minus 2. Alright, so our first derivative is negative 4x cubed plus 48x. And our second derivative is negative 12x squared plus 48. And here I've put in my critical numbers. X equals 0, negative 2 square root of 3, and 2 square root of 3. I've also, in yellow, put in my possible points of inflection, negative 2 and positive 2. And if we, let's go in in yellow. So we have negative infinity to negative 2. And we have from negative 2 to 2. And we have from 2 to infinity. Whereas in red, keep in mind we're looking at these intervals in red. And as long as we have a test point for each of the red intervals, and we have a test point for each of the yellow intervals, and we have negative 4 fits in both of these. Negative 1 will fit in this. Negative 1 will also fit in our interval from negative 2 to 2 as well 1. So I only need to use one of those in the second derivative. And then 4 fits both in this one and this interval with 1 in between 0 and 2 square root of 3. So I need all 4 critical numbers, 4 test points for my first derivative, but I only need 3 test points for my second derivative. And when I do so, I find the first derivative is going to be in red. F prime of negative 4 is 64, so I'm going to be increasing. F prime of negative 1 is negative, and so I'm going to be decreasing. Positive 44 is increasing. Negative 64 decreasing. Yeah, this is looking kind of nasty, isn't it? F double prime of negative 4 is negative, so I'm concave down here. Oop. F double prime of 1 is positive, so I'm concave up. And then concave down again. And that gets horrible. I really should have left myself a little more room, but let's look at what the summary tells us. It tells us we are increasing from negative infinity to negative 2 squared to 3, and then again from 0 to 2 squared to 3. We're decreasing from negative 2 squared to 3 to 0, and again from 2 squared to 3 to infinity. We're concave up in between negative 2 and 2. We're concave down on the outside, so negative infinity to negative 2 and 2 to infinity. Maximum points, based on the first derivative test, we know the maximum points are at the 2 square root of 3's with an output of 144. If you're using WebAssign, you have to write these as separate points. There's no plus or minus, which is good. This is the lazy man's way, and I use the lazy man's way a lot, but as students, you should do it for reals. The minimum point will be at 0, 0, points of inflection at 2, 80. And remember, these y values always come to us from the original function. If you want to test to see if 0 is truly minimum, put 0 into the second derivative, and you'll see that the second derivative is positive at 0, concave up, gives us a minimum. In our graph, yeah, look at that. We have maximums, we have a minimum. Around right here, 2 squared to 3, I would say it's 2 squared to 3, that's my maximum. It's at negative 2 that I'll have a change of inflection. Look to the left, it's concave down. But to the right over here, it's concave up. And then once I get to 2, it goes back to concave down again. So it seems reasonable. We got it right. Let's do another one. Negative, parentheses, x minus 5, all squared. My first derivative, I'm going to bring down the 2. Negative 2 times x minus 5. And if I wanted to, I could distribute that, call it negative 2x plus 10. Because my second derivative is going to be negative 2. A critical number only occurs when x equals 5. No points of inflection. Second derivative is always defined, but never 0. So a critical number of 5... I'm going to use a test value to the left, 0 sounds good, and a test value to the right, 6 works for me. And when I test these, in the first derivative, if I put in 0, I'll get a positive, so I'm increasing. If I put in 6, that's negative 12 plus 10, that's negative, so I'll be decreasing on the right. So if I go from increasing to decreasing, I'll have a maximum at 5, oh, my y value is 0. It is never concave up. The second derivative is always negative. Because the second derivative is always negative, of course I'm going to have a maximum. Right? Second derivative is always negative. Concave down. I'm going to have a maximum value. And my graph. It's a nice graph. Good job. Good work. Find all relative extrema. Use the second derivative test where applicable. Another polynomial, x cubed minus 5x squared plus 7x. Take the derivative. 3x squared minus 10x plus 7. And I can factor this. Why would I choose to factor it? I choose to factor it so that I can easily find my critical numbers of 7/3 and 1. Factors turn into zeros. My second derivative is 6x minus 10. And I set that equal to 0. I'm going to get 5/3. It's a possible point of inflection. So finding the derivatives, setting them equal to 0, and finding where they do not exist, which doesn't apply with polynomials, but finding those two locations, very important. So, I have 1, 7/3, and 5/3. Let's see if I could get these all appropriately on a line. I'm thinking 1, 7/3, and 5/3 is from our second derivative. That's a 5. Ugly looking, but it works. My test values, I'm going to test 5. I'm going to test 2, right, because 2 is 6/3, so I know that works out. I'm going to test 0. 0 is always a good one to test. And that's all I need, because 0 will work to the left of 5/3. Either 2 or 5 will work to the right of 2/3. And I have one value in between 1 and 7/3, a value to the left of 1, and a value to the right of 7/3. So when I test the first derivative at 0, 2, and 5, I end up with positive, negative, and then positive. So increasing, then decreasing, then increasing. The second derivative at 0 is negative 10. Second derivative at 2 is positive 2. This tells me that I'm concave down on the left. Concave down on the left, negative infinity to 5/3. Concave up on the right, because it's positive. Concave up on the right. Because, right, the second derivative on the left of 5/3, 1, this is concave down. I know that 1 is going to be a maximum. Because the graph is concave up on the left, I know that 7/3 is going to be a minimum. And a point of inflection because I changed concavity at 5/3. The y values all coming from the original function. Always back to the original to find y values. And our graph confirms the values we found. We have a maximum. We have a point of inflection about right here. We have a minimum at 7/3. Looks pretty good. Now, let's make it harder. G of x is negative 1/8 times x plus 2 all squared times x minus 4 all squared. Now, this is about concavity and extrema. So I'm not going to focus a lot on the details of the derivative. If you need to pause and make sure my derivative is correct, I encourage you to do so. I'm not always right, I know. It's mind-blowing, but it's true. I make mistakes, and I don't do it on purpose. So the negative 1/8 I left out in front. When I'm taking the product rule, taking the derivative of these two using the product rule, I also have a quotient rule. And I will factor out the x plus 2, the x minus 4, and the 2 that both of them have. What I'm left with. Condense and simplify. I factor out a 2 here to take care of my 1/4, as this 2 took care of my 1/8. So I have my first derivative. The nice thing about this first derivative is that I can easily find the zeros of it because it's in factored form. But now I need to find the second derivative. So here's the original function. I take the derivative of the derivative and I simplify. Again, if you need to pause and make sure you can find every step. I'm not going to necessarily talk through it, or else this lecture would end up being a couple hours long. So I have my function g of x. I have my first derivative. I have my second derivative. I know my first derivative is 0 at negative 2, at 4, and at 1. Possible critical number, those are critical numbers. Possible points of inflection, I want to find where the second derivative is 0 using quadratic formula. X equals 1 plus or minus square root of 3. Notice I call this a critical number because it's guaranteed to be a critical number. But it's only a point of inflection if the concavity changes there. So it's a possible point of inflection, not necessarily guaranteed using our definition. Okay, so now we fill in our number line. Negative 2, 1, 4, 1 plus or minus square root of 3. Where do you think that would be? Well, I know that square root of 4 is 2. And so square root of 3 has to be less than 2. So I know that maybe here, I should choose to use that in yellow. So maybe here, I'll have 1 minus the square root of 3. That's so not true. Let's back that up a little bit. 1 plus the square root of 3 will be a little more than 2. A little more than 2, so maybe we'll put it right there. I know it's definitely less than 4. In fact, it's definitely less than 3. And I could put 1 minus the square root of 3. That's probably somewhere around here. It's a little less than 0. It's negative, definitely negative, but you know, it's got some decimals going on. Now I need to do test intervals. And in my test intervals, we find, using negative 4, 0, 2, and 10. In red, I have my critical numbers for the first derivative. When I evaluate my first derivative in my function, I decided not to finish g prime of 10. G prime of 10 looks like it will be negative, and then positive, 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 so it must be negative overall. Of course, I'm using yellow when I meant to use red. There we go. In blue, I have my possible points of inflection. So I choose any value to the left. -4 gives me a negative. Choose any value between them, and I know 0 is in between them, so I get a positive. And then I choose g of 10, and I get another positive. And that looks weird to me. That looks very weird to me. G of 0 in my second derivative is definitely a positive. 10 squared is 100. 100 minus some stuff, this should be negative. Never trust what you've written. Always talk it through. Make sure you've done it correctly. I forgot about that -3/2 out in front, giving me a negative. And this negative is where my concave down comes from. Concave down. So negative infinity to 1 minus the square root of 3, and then again from 1 plus the square root of 3 to positive infinity. Even though I had the symbol wrong, fortunately, I had the intervals correct. If I'm concave down here, I know that 4 is going to be a maximum. Concave down here, I know that -2 is going to be a maximum. 1 is in the concave up interval, so this will be a minimum. Let's take a look. Maximum points at -2, 0, and 4, 0, maximums. A minimum point at 1, if I put 1 in, I'll get 1 over 1, -81/8. Points of inflection, because I do change concavity at my blue values, and I need to find the y value, so I have to evaluate, and calculators do come in handy here. Looking at the graph, maximum at -2, maximum at 4, minimum at 0. We have points of inflection right about here and right about here. Increasing, decreasing, increasing, decreasing. We have concave down, and then concave up, and then concave down. Everything looks great. Last example. Y equals x over x minus 1. We find the first derivative using the quotient rule. We find the second derivative using the quotient rule with a little bit of chain rule thrown in. And I know the only critical number for either derivative occurs at x equals 1. The numerator is never 0, so the first derivative is never 0. First derivative is undefined when x equals 1. Second derivative, numerator is never 0, so the second derivative is never 0. Second derivative is undefined at x equals 1, but so is the original function. So it makes sense the derivatives will also be undefined there. So it's not in the domain. Something important happens there. So if I have my critical number of 1, I'm going to take any value to the left. Oh, I'm feeling 0. Any value to the right. 2 seems good. And I'm going to evaluate both the first derivative. Denominator is always positive, so that's negative over a positive. And again, when I put 2 in, the negative over a positive. So it's always decreasing, except at 1. Make sure 1's a critical number, so I have to leave it out. The second derivative, at 0, I'll have 2 over -1 cubed, so that's positive over negative. At 2, 2 minus 1 is 1. 1 cubed is positive. That's positive over positive. So I'm concave down on the right. Concave up on the right, positive. Concave down on the left. No extrema, because x equals 1 is not in the domain. It's not in the domain of the function, so it can't be an extreme value. What do we have? We have always decreasing. Always decreasing. X equals 1, not in the domain of the function, so something important happens there. Concave down. Concave up. No extrema, right? There's no maximum, no minimum. Everything looks good. It looks like we got it down. So, first derivative, extrema, critical numbers, minimums, maximums, increasing, decreasing. Second derivative, points of inflection, concavity, concave up if the second derivative is positive, concave down if the second derivative is negative. And looking at this graph, I can't forget to thank, which I have previously, I've forgotten, can't forget to thank Desmos.com for all your graphing calculator needs. Desmos, for your calculator or your computer, you can have awesome graphs like this. No, they don't pay me, but I would accept donations. Thanks for listening.